Have you ever stopped to think about how an AI knows the difference between a dog chasing a cat and a cat chasing a dog? I mean, the words are exactly the same, but the meaning? Totally different. Well, the secret is this hidden little mechanism that gives AI a sense of order, a sense of place. It's a concept called positional encoding. So let's dive in and see how this thing actually works.
Okay, so take a look at these two sentences. Same exact words, but they tell a completely different story, right? For us humans, the sequence is everything. It's the skeleton that the meaning hangs on. But here's the twist. For some of the most powerful AI models out there, like transformers, this is a massive problem. They're built to look at all the words at once, which is a big deal. So how do they get around that?
The core issue has this kind of fancy name, permutation invariance. But all it really means is that, by default, the model is completely blind to the order of words. Without some kind of fix, the dog chased the cat looks like the same jumbled up bag of words as the cat chased the dog. The model sees the what, it sees dog, cat, chased, but it has absolutely no clue about the where, and that's the puzzle we've got to solve. So how in the world do you teach an AI that's blind to order all about sequence? Well, the solution is surprisingly elegant, and honestly, at its heart, it's a really simple idea. We're basically just going to give every single word a number to mark its place in line. You know, the best way to wrap your head around this is with an analogy. Imagine your sentence is just a bunch of Scrabble tiles you've thrown into a bag. You pull them all out at once. You've got the words, sure, but you have no idea what the original sentence was. Positional encoding is like we decided ahead of time to just write a little number on the back of each tile, first, second, third, and so on. Now, even if they're all jumbled, you can instantly piece the correct order back together. Simple, right? Okay, so how does that Scrabble idea actually work in the machine? Well, for an AI, every word first gets turned into a list of numbers. We call this its embedding vector that basically captures its meaning. From there, it's a super simple three-step recipe. First, you take that vector for the word's meaning. Second, you cook up a brand new vector that only represents its position. And third, you literally just add those two vectors together. What you get is a new combined vector that knows both what the word is and where it is. But wait, how do we create that special position vector? We can't just use plain old numbers like 1, 2, 3. That's too simple and causes problems down the line. We need something a little more sophisticated. And this is where, believe it or not, a little bit of high school math comes to the rescue. We're going to use sine and cosine waves to create what is basically a magic formula. And here they are. These two equations are the entire engine behind this whole thing. Now, don't get hung up on the math or try to memorize it. That's not the point. The key takeaway is that by switching between sine and cosine functions that are moving at different speeds, we can generate a totally unique numerical signature, a special vector, for every single position in a sentence. It doesn't matter how long that sentence gets. You know, abstract formulas are one thing, but seeing it in action really makes it click. So let's just walk through a really simple, concrete example. Let's use the sentence, the cat sat. We're going to build the final inputs for the sentence step by step. All right, first things first. Every word starts out as a vector that represents its meaning. So here you can see some made-up embedding vectors for the, cat, and sat. Just think of these numbers as a set of coordinates in some giant meaning space. This is our starting point. This is the what. Okay, next up, we use those sine and cosine formulas to generate a totally unique vector for each position. Position 0 for the, position 1 for cat, and position 2 for sat. These vectors you see right here, this is that positional spice we're about to add into our recipe. This is the where. And for the final step, we just add them up. We take the meaning vector and the position vector for each word and combine them. And that's it. We have our solution. This final set of numbers you see here is what actually gets fed to the AI. And inside these numbers is this bundled information about both what a word means and exactly where it is in the sentence. So we can see that it works. But why this specific approach? Why all the fuss with sine and cosine waves? Well, it turns out this design isn't just random. It has some incredibly clever and powerful properties that make it perfect for this job. It really boils down to three main reasons this is so genius. First, every position gets its own totally distinct numerical signature. It's unique. Second, the relationship between positions is consistent, which is huge, because it helps the model understand not just where a word is, but where it is in relation to other words.
And third, it's generalizable. Because these waves are periodic, the model can often figure out how to handle sentences that are way longer than anything it was trained on.
Let's just zoom in on that idea of consistency for a second, because this is the really clever part. The magic of using sine and cosine is that thanks to their mathematical properties, the position signal for, say, position 7 can be calculated directly from the signal for position 5. What that really means is the model can super easily learn concepts like 2 words apart or 5 words before, which, as you can imagine, is absolutely critical for understanding grammar and context.
Of course, in the world of AI, things never stand still. The original breakthrough idea was to add these static position signals right at the beginning. But the latest AI models are using even more advanced tricks, like something called rotary position embeddings, or ROPE for short. These new methods basically inject the position information directly into the model's core brain, its attention mechanism, making its grasp of relative positions even stronger and more powerful. So when you boil it all down, the crucial point is this. We started with a simple but huge problem, that AI models see words as just a jumbled mess. And it was solved with an incredibly clever mathematical key. Positional encoding is the fundamental insight that taught these order-blind machines how to finally read a sentence and understand the beautiful and absolutely critical flow of human language. It's really an amazing leap forward. By figuring out the where, AI got so much better at understanding the what. But it does leave us with a pretty fascinating question to think about. Now that AI is getting a real handle on sequence and structure, what's the next great challenge in its journey to truly understanding the why behind our words?